Hi, everybody. It's Miss Austin, and I'm going to be doing the Lesson 8 practice problems with you. Here we go. It says match each polynomial with its n behavior. Some n behavior options may not have a matching polynomial. So what we learned is that if the degree is even, that the n behaviors are both getting bigger and bigger in the positive direction. That's for an even. And if it's an odd degree, it's getting bigger and bigger as x gets bigger and bigger in the positive direction, but it's getting bigger and bigger in the negative direction as we go this way, okay? And I circled the ends because, it can do all kinds of different things in the middle, but what we're looking at is what happens at the ends. So here we go, letter A. I look here, this is a fourth degree polynomial, so no matter which way you travel in the x direction, if you get bigger and bigger positive or bigger and bigger negative, your output values are getting bigger and bigger in the positive direction. So that's this match right here. As x gets larger and larger in either the positive or the negative direction, f of x, which is your output, gets larger and larger in the positive direction. So this one goes to number 1. All right, let's look here. Letter B is also an even degree. So it's the same thing. No matter which way I travel, the graph is going to get bigger and bigger in the positive direction. All right, letter C is also an even degree. I'm just making sure that all of these are really supposed to be number 1, but it is. C would look like this again, and if you were confused, you could always go to Desmos and type it in real quick and see. Okay, this is an even degree. No matter which way I go, if I go to the right or to the left, the output of my graph is getting larger and larger in the positive direction. All right, letter D is 1. That's an odd, and hopefully you might remember that's just a line, right? Y equals mx plus b. I'm just going to show you what that picture would look like down here. Be positive 5, so the line would be going like that. See how the ends are going in opposite directions? So as I get bigger and bigger in the positive direction, my graph is getting bigger and bigger in the positive. But as I get bigger and bigger in the negative direction, my answers are getting bigger and bigger in the negative. So let's see. As x gets bigger in the positive direction, y gets larger in the positive, yes. As y gets larger in the negative direction, the output gets larger. This one is number 2. Let's just make sure. What did these two say? Yeah, these are backwards. Maybe those will show up today. All right, so A, B, and C all were number 1, and D belonged to number 2. Number 2, which polynomial function gets larger and larger in the negative direction as x gets larger and larger in the negative? So imagine if you're walking this way, right? The graph is down here. Well, what did we learn today? That's an odd degree, right? It's got to be an odd degree. So this isn't even, no. This is an odd. Let's just double check. Even, no. Even, no. This is the only graph that has an odd degree, which would have n behavior described this way. You could also type those into Desmos to double check. Number 3, the graph of the polynomial function f is shown. Which statement about the polynomial is true? The degree is even. If the degree is even, then no matter which way I go, right or left, right? I'm getting bigger and bigger in the positive or bigger and bigger in the negative. My outputs are both getting bigger and bigger in the positive. That seems to be true here. That's what's happening. Yes, it dips down, but I'm looking at the ends. Could not be odd. The constant is even. The constant, we haven't really talked about this, but it ends up being the y-intercept. And it looks like it's like 3.5, so that isn't correct. And the constant is odd. Maybe they didn't want to talk about that today. But for sure, the degree of the polynomial is even. Number 4, here's the infamous box problem. Andre wants to make an open top box by cutting the corners of a 22 by 28. Show the visual here, 28, 22, and I'm cutting corners out. Write an expression for the volume. Volume is length times width, and then if I fold up those corners, height. Okay, so this is going to be 28, take away, these are x, 2 of those. This dimension is going to be 22, take away 2 of those. And then when I fold these up, there's my other dimension. I'm going to put it out front. Factored form polynomial. What is the volume of the box when x is 6? Well, I'm just going to put a 6 here. If I put a 6 there, that's 12. 28 minus 12 is 16. If I put a 6 there, 22 minus 12 is 10. So, calculator, 6 times 16 times 10, 960 cubic inches. What is a reasonable domain? Well, that's just asking how much can I cut? So you look at the shortest dimension, which is 22. So you can start cutting anywhere from 0 inches all the way up to half of that, 11. Number 5, for each polynomial, rewrite it in standard form, then state its degree and constant term. So I'm going to do a box real quick here. 3x plus 1 times x plus 2, 3x squared, 3x, 6x, 2, that becomes 3x squared. Those 2 make 9x plus 2. So I've done those 2. Now I need to multiply by the x minus 3. I've got 3x to the third, 9x squared, 2x, negative 9x squared, negative 27x, negative 6. So now my final answer for this guy is 3x to the third. The x squareds cancel. Negative 25x minus 6. So now there's my degree. And negative 6 is my constant. All right, letter B. It's the same exact problem, but it's got a negative 2 out front. I've already done the multiplication for these 3. It's right here. Now I just need to multiply that whole thing by negative 2. So let me show you that. I just need to multiply each of these by negative 2. That would become negative 6x cubed plus 50x plus 12. Still a third degree, but this time the constant is 12. All right, last one. Number 6, Kieran wrote f of x equals x minus 3 times x minus 7 as an example of a function whose graph has x-intercepts at x equals negative 3 and negative 7. What is his mistake? So if this touched at negative 3 and negative 7, right? Those are the values that turn the equation into 0. If you put a negative 3 in there, negative 3 minus 3 is negative 6, right? So Kieran's mistake is he's just looking at what's in the parentheses and saying, he's going backwards. He's supposed to write a function that has these zeros. So I've got to think of, if it touches at negative 3, what did the factor look like? It said positive 3. And if it touches at negative 7, then what did the factor look like? Positive 7. His mistake is he's just taking those and putting those right in the parentheses. Now look, if it touches at negative 3, if you put a negative 3 in there, that turns out into 0, and 0 times whatever that is, doesn't matter, is 0. That's why the point on the graph is negative 3, 0. would say you didn't switch the signs so they would create a 0, something like that. All right, we cut off 7 to save time. I hope that helped. I'll see you soon.